Hi, I'm Justin, G0KSC, and thanks very much for joining me once again. Second day in a row for making one of these videos, and that's really after the love I was shown after yesterday's video, and from some very big and popular YouTubers as well. So that inspired me to get up a little bit earlier today and prepare this, which I'm going to present to you now. It was one of the subjects which I said that I will extend upon and was expecting to probably do it next weekend. But instead I've done it today. It's very windy out and not an ideal day for going out and playing anything to do with antennas whatsoever. So it's just been literally sat on the drawing board this morning and playing around with that to describe what I want to do with regards to chokes. Now, the reason I'm picking on the choke balun, ugly balun, one-to-one coiled coaxial balun, whatever you want to call it, is that there are a lot of misconceptions and errors that are made when not just building chokes but also installing them. Now, there are a number of considerations to make which I touched on yesterday. One of those is that the effective bandwidth of a choke is relatively narrow. That's the first thing. The second thing is that depending on the coax you use depends on the effectiveness of the choke, how high the impedance can become and whether it actually works or not. And ironically, some of the better quality coaxes are not very good for producing chokes. And the main reason for that is that the capacitance, or the C, the effective C between the turns in the choke, are not where they need to be to provide the expected and required capacitance between the turns. And that generally tends to lend itself, worsely, if that's a correct expression, to chokes which are made of high quality coax, because the outer sleeving tends to be thicker. So quite often, especially when you're looking at VHF and up, it should be a good quality coax but a smaller diameter, something like RG174 with silver plated wire and a fairly thin overall size. I think it's about 6 millimeters, something like that, isn't it, a diameter of that, because then you can make a balun or a choke that is going to work. Now, you will need to use one of the calculators if you haven't got the ability to test the choking impedance of the choke. And if you're measuring it, we can go into this in another episode if need be, but effectively you need to measure the choking impedance of the outer braid of the choke side to side. You're not touching the middle section at all, or the inner core of the coax at all in the measurement. It's just the outer sleeve to see what the effective choking is. Now, the good things with a choke balun is that you can get extremely high impedances and much higher than you require to prevent those common mode currents. So they can be extremely effective. However, and the subject of what we're going to cover today explains that quite often that ability for the choke to be effective is often mitigated by the proximity of things like booms. So I've just got my page open on here for Innov Antennas. If anybody doesn't know, that's my business and where I operate from. And also g0ksc.co.uk is my free to build site, and that has some of my very early designs on those, where you can go on and pick a design and build it. They're sort of now, what, 13, 14 years old, something like that. Now, what I am doing, as I've mentioned in some of the recent videos, is I'm going to be starting to present some of the very latest designs that have only been available through Innov Antennas on YouTube, and give you specific and dedicated download locations to produce or to receive the drawings for building those antennas. So we'll see how that goes and to whether we continue with that any further. So what I'm going to do is I'm going to first off open my drawings that I've been doing in Canva to give you some of the typical ways in which a choke is installed on the boom, or in a Yagi scenario. Now, one of the reasons for showing this is that there are even commercial antennas that are made this way, where the function is going to be impeded as a result of being used like this. So this is a typical configuration. This is a boom. I've put the boom effectively, if you like, upside down so that the insulators in this case are facing downwards. This is, if you like, representative of, say, a HF antenna, because we have the element holder plates as well as the element holders, the insulators that you can be seen here. That's the boom itself, the element holder plate, the element holders, and they're in different places. Now you wouldn't have two feed points in different locations, but rather than do two sets of booms with two different configurations of the balun, I've just put them in two different places here, so that you can get an idea as to how that should look, or how, not how it should look, but how it typically looks in a normal installation. So this is what would normally be the case. It would be installed at the feed point. There's a length of coax before the choke starts, then the turns of the coax, and then the feed line, which would go back to the shack or wherever it is that's going. That's example one. The second one is where the choke is upturned, so it's standing vertical, if you like, and the coax, again, there's a fairly long section of coax, comes from the feed point to the start of the choke. Then you've got the turns, and then it comes off of that, and then it feeds along the boom. So this is that's the first instance. We'll come on to that or into a little bit more detail in a moment. Now the second point on connecting the coax to the feed point, it is quite common for us to install the terminal connections quite close together. Typically I would use, say, a gap of around 10 millimeters on VHF antennas and maybe 20 millimeters on a HF antenna between the two sections of the driven element. Now, just to cover one question that I get offered or answered quite a lot in this instance, and that is, with that gap, if I have, say, a 10 millimeter gap, do I add 10 millimeters to the overall length of the dipole? Or if I put a 20 millimeter gap, do I add 20 millimeters to the overall length of the dipole? The answer is no, you don't. What you're effectively doing is taking that section out. So if the overall width of this dipole was 2,500 millimeters, then regardless of whether you had a 10 millimeter gap or a 20 millimeter gap, the overall width would be still 2,500 millimeters. So why is that? It doesn't matter where these terminals are. The dipole, if you like, the ideal dipole is one that's just fed, it's getting its RF from a source. It's not actually connected with coax, it just arrives and then it radiates. The necessity for the break in the middle is so that you can connect a feed line to it in order to feed the antenna or the dipole with current. So the towers between the coax cable and the dipole itself are a part of that driven element. So they are effectively filling that gap. So it doesn't matter how much or how big that gap is, they're filling the gap. And that's why, as I explained yesterday, you need to have those towel connections as much in a T-shaped as possible rather than a Y-shape across those terminals. So you're not putting a V into the center of the dipole, you're keeping it into a T-shape. Now I need to put something into perspective here, which is quite important. When we're looking at antenna, not so much the antenna design, but the replication of an antenna design in the real world, you need to factor in sizes in terms of wavelength, not the physical measurement. So what do I mean by that? Let's say, for instance, you have a 20 meter Yagi and it has 2-inch towels between either side of the coax cable to the dipole center. That 2 inches of tower overall, which would be 4 inches in total, is a very insignificant amount of length in terms of wavelength, in terms of that 20 meters wave length from one part of it to the where it starts again. If you was to transfer that 2 inches to 2 meters and you had 2-inch towels on a 2 meter Yagi, it's still 2 inches, but it's the equivalent of having 20-inch towers on 20 meters. So just to explain again, that 2 inches worth of towels on 2 meters is the equivalent of having 20-inch towels on 20 meters. So, just think about that for a second. If you were going to be installing a 20-meter Yagi, would you have 2 lengths of wire from the center of the coax that were nearly 2 foot long to connect to each side of the dipole? No, of course you wouldn't. So whilst that 2-inch towels might be okay on 20 meters, it's certainly not on 2 meters, and it should be as short as you can possibly get them. And the more that replicates that T-shaped across the feed point, the better and closer to the model replication you will get in the real world. And whilst, as I mentioned just a second ago, that the 20-meter antenna would be okay with those 2-inch towers, if you know this is best practice to get the feed point as short and as much of a T-shaped as possible, then why not just implement it on whatever band it is? So just coming back to this drawing that we're explaining here, if these were only 10 millimeters either side of that dipole center, and whether this is 2 meters, 20 meters, or whatever band it's for, you only have 30 millimeters between the terminal sections here. So that would be very difficult at the best of times to get that V-shaped connection. So it may be that you need to open up a little bit wider. So that's always something to consider and have a look at as you when you're considering building your antenna. So I showed down here the scenario of what is not the right way, but really didn't explain why. So we're going to do that now. This is how really the choke ideally would be installed. Yes, it might be that it's rotated so that it's coming down, so it's got a more natural route downwards from the feed point rather than upwards, as is explained here. And what I've done is I've done a cross-section view, so effectively the insulators that you can see here are now translucent here, and you can see that what I've done to accommodate the angle of exit of the choke balun, I have rotated the dipole center so that we now have, say, a 45-degree angle on those terminal connections, in order that it's a much cleaner connection to the input of the choke, and to better place the choke for coax exit that's then going to loop back and run along the boom. So why is it important to do this and not this? As you probably know, the choke is it's a coil, and it's an inductor in a sense. So in order for that to work correctly, you have a magnetic field flow through and around the coil, which is giving you that choking impedance. This is from sort of, as I've said right at the beginning, and in the explanations as to some of the videos that we're going to be doing here, rather than going into detail in theory, I'm explaining these as best as I can so that anyone of any level can understand what's going on and why it needs to be done the way it is. So if this electronic or magnetic field is flowing in and around the coil, and then you place it up against, either this way against a metal surface or this way against a metal surface, then you impede the ability for that choke to function correctly. Now, if you had an electronic circuit, whether it a radio receiver or what have you, and there's some tuned circuits in there with some RF chokes that are or inductors which are on the board, and you was to put a screwdriver alongside them or a metal surface, you will see that things change drastically. So wherever you've measured that inductor, or if you've measured that choke outside of the realm of the antenna, and then you put it up against an anomaly that wasn't there in the test and measurement when you was establishing whether your choke worked, like in this instance where it's up against the boom, then the chances are it's no longer going to function very well at all. And if it does have some sort of functionality, it's not going to be where it was when you were testing it in the first instance. So that's that part. Now the second part on here when you're considering the choke is this section. I'm just going to blow this up for a second, and we'll bring this down. And whilst this is coax cable, and it's not a split towel in this section, let's just move the arrow up so that we're pointing at it. Whilst this is still coax cable and it's not the split towels which I said would be radiating, what you need to consider is, if you go back to the video that we presented yesterday, the first one on baluns, and if you haven't seen that, I do recommend that you watch that one through, that when you connect coax to the feed point of an antenna without a balun, then the RF has no intelligence and it doesn't know where the beginning of the antenna starts and where the coax stops, and vice versa. So the current can flow back along the outside of the coax from the cold side. Okay, so this choke that you've wound here is preventing that coax radiation. It's stopping that RF from traveling along the outside of the coax, assuming it's wound to the right dimensions for the frequency, in order that you have no coax radiation here. However, that choke here doesn't have any choking functionality on this part of the coax. So this part of the coax is still an extension of the cold side of your dipole. So if that doesn't make sense, let's just bring this down to a smaller size. I want to come back to that one in a moment. This is the cold side of the coax as we were representing it. So this section, if it's feeding the antenna on this side, is still hot on the outer sleeve. This side after the choke is fine. So if you've got 6 inches of towel between the choke itself and the feed point, then the outer sleeve of that piece of coax is still radiating. That's still a part of the dipole. So to take that and put that into perspective, let's say for instance this is our dipole now, and we are feeding it at the side here. You can see obviously the insulators, the element to boom plate, and then the element itself. And everything in blue is representative of the RF that's in here. So where the hot side is connected, which is on this terminal here, the hot side goes straight inside the coax and the inner sheath, so it can't radiate anymore. So the effective radiating width of the hot side of the dipole is from this point here to this point here. That's fixed, no problem. Now, this is a representation of your coax with the choke balun, and then with the extra piece of coax that goes up where both terminals are joined. Now in this instance, if that's 6 inches, your effective cold side of the dipole starts here and finishes here. So now you have a vertical section by that length. Now if this is also effectively a radiating part of it, and that's now up against or close to the boom, what impacts is the boom having? Is that now some sort of decoupling going on? You'd need to model it and see what happens. You could do this quite easily in EasyNet, because you could add this extra piece of wire here and then run an extra piece of wire underneath it of say 2 inches to replicate your boom, so you can get an idea as to the effectiveness of that section and what it's doing to negatively impact the antenna. So worst case, it's going to still radiate, it's going to still get SWR, it might not be quite as low as what you were expecting, and if that lead wasn't there, but at the very least you've now unbalanced the feed point, because you're now not feeding the antenna effectively at center. It's kind of a skewed feed that you've added to the antenna. So now it could mean that the forward lobe is slightly lopsided, and you have odd or uneven back lobes from the antenna as well. So it's something to consider, it's something to look at. And again, as I mentioned right early on in the presentation here, if this section can be made as small as possible with the T-shaped connections on the coax as much as possible, let's bring that up inside, so that you have your ring terminals to bolt onto the feed point. And what I recommend that you do here, rather than sort of guesstimating what the width of those terminal connections are, if you're using something like RG213 for your dipole connection, and bearing in mind that you've got your braid with your terminal connection to the ring terminal, then the center core going to the ring terminal, and then of course you've got a little bit of the insulated dielectric to separate these, and bearing in mind that these all need to be wrapped in self-amalgamating tape, and then perhaps insulation tape, and then maybe painted with Inadvertently's rubber seal, which gives you that second RF or UV protection, I should say. When you've done that, or when you're doing that, what I would suggest that you do is to produce this first and see how small you can physically get the distance between these 2 points, the center of that ring terminal and the center of this ring terminal, without compromising the arrangement, without the insulation gap being too small, in order that you could get some flashing. 5mm or something like that is great in HF installations, maybe a little bit lower than that if you've got relatively low power examples on VHF and up. But you know, if this is something that people want to see, we can discuss this on certain different frequencies and best practices here. So I would produce that, see how small you can get it, and once you've got that and you measure that distance, now you have the ideal distance that you need those feed point terminals to be apart at that feed point. So I'm just going to recap on a couple of things here. The terminals, as much of a T-shape as possible. Practically it's very difficult to make them in a real T-shape due to the way that the coax is arranged. What you can do is you can cut the coax effectively at a 45-degree angle, so you can have the one side coming out here and then the other side coming out here. But what the benefits are electrically, I don't know. There's not a great way of measuring that, so this is the most practical way of doing it. The second thing is that if you're installing a choke, a coaxial choke onto any antenna, whether it's a dipole or anything else, remember that you've got to respect frequency. It's not the physical measurement that counts, it's the percentage of wavelength that you need to consider. So a 2-inch towel here at 20 meters, if you had is very small and it's an insignificant part of wavelength. But if that 2-inch towel from these parts was placed on a 2-meter antenna, it would be the equivalent of having a 20-inch towel section between here and here on 20 meters, which you just simply wouldn't do. So just make them as small as you possibly can. The choke should exit the feed point at an angle. It doesn't matter if this coax rotates back and comes back to the boom and lays on the boom, because it's now completely cold on the outer sleeve. You've got no issues. And the best route for this is for this to do with the elements and the insulators below the boom, so it's a nice natural downward exit from the feed point and back again. So why do we do that? We do that so that the magnetic flow in and around the coil is not impeded by any metallic structure, in this case the boom, which would be depicted here. This is some of the common methods that people fit the chokes on the boom in where it will be impeded. So if they were lifted away from the boom, and maybe a perspex or perspex structure to, perspex wouldn't be perfect, but a Delrin structure, something like that, to hold the coax away and the choke away, then that would be best practice in that instance. So that's pretty much it. Hopefully that's going to be of use again. If you've got this far, congratulations, you've made it to the end of another video. And if you've got any questions, please post them down below. And I promise, cover the J-pole and how to get that lower angle of radiation and slightly higher amount of gain in the next video. If I don't get this done during the week, then it will definitely be next weekend, so look out for it. Until then, see you soon.